Hello everyone, now we will be discussing about the compressibility of the rock. So compressibility of the rock is, as it is said to be, is the compression in the volume of the rock due to the overburden pressure. The overburden pressure is said to be increasing of 1 psi per foot in normal conditions, while the pore pressure, which is actually the overburden pressure which is reaching the fluids in the pore, is said to increase 0.5 psi per foot. So this is an important constant to be remembered. Apart from that, we have effective overburden pressure. Now effective overburden pressure is the pressure that is being applied on the fluids within the pores of the rock. If there is a porous rock, then the pressure that is actually coming onto the pores, the fluid of the pores, we call it effective overburden pressure. Now this pressure is actually a subtraction between overburden pressure and internal pore pressure. Internal pore pressure is the pressure handled by the rock or the pore. So, and overburden pressure is the actual pressure that is coming from upwards. So the pressure that is actually applied on the fluid would be equal to the pressure that is coming, the total one, and the pressure that is being faced by the rock itself. The remaining one would be faced by the fluid within the rock. Okay, next point that we are going to see is what happens during pressure depletion. Pressure depletion is reduction in you can call it as pore decreasing of pore size due to uh, movement of the pore fluid. For example, if we have oil in the formations and we are producing the oil, then the pore pressure which was being faced by the oil would be zero because oil has moved. So what would happen is that these pores would collapse, the rock matrix would decrease. That would be, whether we call it pressure depletion. In that condition, pore pressure decreases because fluid is going, so there is nothing to face the overburden pressure, so pore pressure is decreasing. Effective pressure is increasing because uh, no more resistance is coming on its way, so it gets increased. And reservoir rock volume decreases because the collapse of the rock due to traveling of the fluids within the rock outside. So as the fluid has gone outside, we do not have the same rock volume anymore. Yeah. And then we have during and then we have okay, sorry for it. Let's just continue. Okay, now let's go. Now let's go. Now we have another new concept which we call it as formation compressibility factor, CF. Now its value is always seen to be between 3 into 10 power minus 6 to 25 into 10 power minus 6. So it is between 3 to 25. It doesn't cross this range, it stays in between. So compressibility concept was introduced by Geertsma in 1957, and he said that there are three types of compressibilities. One is the rock matrix compressibility, that the material from which the rock is made actually gets compressed. We call it the rock matrix compressibility. And then we have the rock bulk compressibility. It is the reduction in the volume of the bulk of the rock, including the volume within the pores. So we are considering the empty volume as well as the rock's own volume. Then we have pore compressibility, which is the reduction in the empty space within the pores. Now this is the constant formula of compressibility. It's always like that. um, it is also the basis for the definition of the compressibility, which we call it as change in volume per unit original volume per unit change in temperature per unit change in pressure. So originally it is like 1 upon V into dV by dP. However, the formula contains a negative sign because volume and pressure have inverse relation between them. As we increase the pressure, volume decreases, and as we decrease the pressure, volume seem to be increasing. Now, if here we are talking about pore pressure, then in case of pore pressure, in case of pore volume, sorry, in case of pore volume, it is nothing but the porosity. So if so, this way we can also replace this formula by porosity, which is phi, and the formula becomes 1 upon phi d phi by dp. But the negative sign is no more because there is not that much relation between pressure and porosity. So the interlink between these three types of compressibilities, rock matrix compressibility and rock bulk compressibility, are in very small uh, amount, or you can say magnitude, as compared to pore compressibility, because pore is a it is an empty space. Pore pore is an empty space. It does not contain anything inside, while the rock itself is made of matrix. It is made of solid matter. So compressibility in pore would always be greater than the compressibility in the rock matrix and in the bulk itself. So how can we calculate the reduction in the porosity by pressure depletion? Because as you produce more and more oil or gas, then uh, pore volume decreases because your fluid is no more there. So as a result, porosity also decreases. However, I said that there is no link out here, which I'm sorry, I was mistaken. I don't know why there is no negative sign, but there should be a negative sign out here. Maybe it's a mistake. So if the pressure change by the porosity change by pressure depletion is to be measured, it would be equal to the new changed porosity would be equal to original porosity multiplied by 1 plus compressibility factor into difference of pressures, the current pressure and the original pressure. We are subtracting them like this because current pressure is greater than uh, current effective pressure, it is saying, which is greater than the earlier one. This is the formula of the total compressibility factor. It is always equal to formation compressibility plus uh, oil compressibility and S naught, which is I think the saturation of the oil, the amount of the oil in percentage, in fraction, sorry. Uh, so um, oil uh, oil oil compressibility factor into oil saturation plus water compressibility factor into water saturation plus gas compressibility factor into gas saturation. This is one of the very important formula when it comes to petrophysics. This is used in transient flow when the fluid is moving within the porous media in the rock. Then this formula is used because compressibility is very much linked to it. And then we have material balance equations in different correlations, which also use this term CT. So now going on, in lab, how do we measure the compressibility? What happens in actual condition is that the pressure within the rock is greater and the pressure coming from outside is less. Alright, so when the rock in stationary condition, and there is some compressibility to be measured and some movement comes inside it, more new oil moves in, then there is also compressibility faced inside it. However, in lab we cannot do it. We cannot access the fluid inside the rock. We cannot move it inside, but what we can do is that we can move the fluid from outside to the rock. So that's what it explains, and that's what we do. We move the fluid from outside within the rock from all the sides, and we try to compress it and see the amount of compression in it. So this experiment is performed like, first initially we have an oil saturated core, for example, and then we leave it within the water bath, in which is called a spontaneous imbibition in which the water itself leaves the rock, and oil itself leaves the rocks, and the water comes in, and then we measure the time that it took, and then we start forced removal, in which we apply the pressure of the water in order to remove the remained residual oil. And in the second phase of the experiment, we move the water now by oil. We just pour the water saturated rock into the oil chamber in the container full of oil, and then we do spontaneous imbibition, in which all of the uh, water inside the rock moves out and oil moves in, and then we remove the remaining water, which would be residual water, and we measure the amount that came out and the time that it took. So there are certain problems of compressibility in which you are required to calculate compressibility factor CF, which can only be calculated by the value of the curve which I will be telling you about, divided by the pressure at that particular point you want to measure. This is a particular curve that would mostly be given to you in the compressibility problems, but it contains pressure on the independent x-axis. It contains VD values, okay, volume the displaced, and there we calculate VD values, which are also called as value from the curve, and we put in the formula, we get the value. For example, if you don't have that graph, and you can use this formula, you can use a value of the curve you can get from volume expelled, right? You would get it from the into the data of the problem, and you would have to divide it by the average pore volume of the rock, and then you would get the value from the curve, which would be again divided by the pressure of the particular rock, that is the pressure that is rock facing, and we'll get the compressibility factor. Next we have correlations to measure it. We have two correlations. One is Hall's correlation, other is Newman's correlation. Hall's correlation is simply I just try to change it a bit. Let compressibility factor be equal to 2 into 10 power minus 6, just consider it, and 5 power 0.4. so you just need to put the value of porosity, and you get the value. While in Newman's correlation, CF is equal to A divided by 1 plus BC 5. So again the phi is just required, and ABC are the values which are different, and this is only limited to consolidated sandstones and limestones. So sandstone and limestone are only the cases in which it works. A's value is 10 into 10 power minus 5, and B is 0.7, C is 80 in case of consolidated sandstones, and limestone is A 0.85, B 1.08, and C 2 into 10 power 6. Alright, this is the end of the compressibility lecture. Hope you liked it.